Okie, good morning, chemists. We'll get started and jump right back into things. Chapter 13, we're going into the nitty-gritty details of making solutions. So we, to reference ourselves, think about like the solutions we made in lab. You know, when you go to the cart and grab the 3 molar sodium hydroxide, those types of solutions. Let's keep that in the back of our mind as we go through these crazy details of solution chemistry that you may not have thought about previously. So in Chem 1210, you know, we worked with solutions. They had concentrations. In the previous slides, we looked at the solution process, thought about intermolecular forces, but also remember, do we remember this table? Yeah, do we like this table, not like this table? It all right. As long as you know how to use it, right? What did we use this table for? We used it to predict the physical states of a double displacement reaction. If you have a cation and an anion as an ionic substance, we are able to look at this table and say, oh, anything that contained like nitrate containing compounds. These were aqueous in solution. When we did the double displacement, that we saw, oh, okay, this substance falls under that part of the table, it's aqueous. Versus if one of your products was fell under this part of the table, then it was a solid, all right? And then that's how we predicted precipitation reactions, which is a type of double displacement reaction. So we're going to expand on this. All right, this table says all nitrate containing compounds are soluble in water, but to what extent? You know, how far can I push that? How much sodium nitrate can I add to water before, hey, maybe at a certain point there's not enough water molecules to dissolve all of the solid that I add, and that is what we're going to look at. We are looking at saturated solutions. So let me just expand on that kind of storyline, that picture diagram that I mentioned. We can add solid to water. Usually when we add solid to water, it dissolves, but at a certain point, maybe it stops dissolving. All right, so here's a picture. We have pure water over here. Let's add a little bit, let's say sodium chloride, all right? This is sodium chloride. So before I drop that little bit of salt into water, let's think about what properties this pure water has. Does this pure water conduct electricity? No, right? Because H2O is a molecular compound. There are no free ions in molecular compounds, so this solution does not conduct electricity. So now let's throw in a little bit of NaCl, okay, salt. Our human intuition says what happens when we sprinkle a little bit of salt into the water and mix it around. It dissolves, yes. So we're using chemical language already. We're saying dissolves. But, you know, maybe to like a child, when they do that, they go, oh, the salt disappeared. But did it disappear? No, it just completely dissolved into the solution. We can prove that salt is there because now once we make that saltwater solution, what about this solution? What kind of properties does this one have versus that pure water? This one conducts electricity. Yeah, so we can prove that, no, those the sodium cations and anions, they are in there. It didn't disappear. They're just now fully dissolved to make a homogeneous solution. We could calculate the concentration of this if we wanted to, right? Okay, so let's look at this picture. Now, what if we added another little spoonful of salt? Do you think it would dissolve? Yeah, probably, and that's what this next picture is. So when we added some salt, it dissolved. Let's add a little bit more solute. It also dissolves. Okay, so I'm going to add a little bit more salt. It too completely breaks up. Now we have free ions in this picture as well. Let's compare the conductivity of these two pictures. Do they both conduct electricity? Yeah, but are they different at all? Yeah, one probably conducts more electricity than the other just because there's more ions present, all right? So that's, again, proof that we're dissolving even more of that salt. It's not, the salt is not disappearing, all right? It's dissolving, it's becoming a homogeneous solution. Okay, now let's kind of push it to the extreme. Let's add so much solute. Right, let's add so much solid that what is different about this picture than the rest of them? There's this hunk of solid at the bottom that doesn't dissolve, right? That hunk at the bottom, I shake this container, I agitate it, I yell at it, but that hunk of solid stays at the bottom and it doesn't go anywhere. All right, so now at this point we have a new type of solution. These ones, you know, these are the solutions we worked with in lab. We calculated their molarity. But now, once we have undissolved solid at the bottom, now we've made what we call a saturated solution. We've kind of pushed it to its limit. We've pushed the water to the limit where it cannot hold, it cannot dissolve or solvate any more solute particles. So what do I want to write here? When even more solute is added, no more solid dissolves. All right, to a certain extent. Okay, let's pretend, let's throw another spoonful of solid into this picture. What do you think will happen? Will it dissolve? Nope, it's that solid's gonna also sink to the bottom. Even if we add another spoonful, it's gonna sink to the bottom because we've reached the limit, the capacity that water has to dissolve this specific solute at this temperature. Okay, so let's pretend we did this in the kitchen. Let's pretend we were making some, you ever make like Jell-O, like the Jell-O mix, or like Kool-Aid, okay? Where you have the powder, you mix it with the water. And the whole idea of like making Jell-O or making Kool-Aid is that you want to dissolve that, you know, the pre-packaged powder. You want to get it all dissolved so you make a homogeneous mixture. So let's pretend we do that. Let's take a Jell-O packet, dissolve it in water, we agitate it a lot, but unfortunately we have a hunk of solid sunk at the bottom that we can't get to dissolve. As much as we shake it, it does not dissolve. So not even as a chemist, just think about like being a regular human being. What would you do to try to get that solid to dissolve? I'm thinking of two different things you could do. What's the first thing that you could do? Add more water. Yeah, adding more water might get that solid to dissolve. Great. What else could we do? Heat it up. Heating it up also is a way we could get that solid to dissolve. So hopefully you know, are putting yourself in the kitchen thinking that. But really what we're doing in the context of chemistry is by heating up the solution, we're actually changing the solubility of the solid, that we give water a larger capacity to dissolve more solid at higher temperatures. Adding more water brings more water molecules to the equation to go in and break apart solute particles. All right, so there's two ways we could get this solid to dissolve: add water, add more water, or heat it up, and we'll explore both of those. All right, so of these pictures, these two are the only ones that are what we call saturated. Saturated. These pictures, these are unsaturated solutions. When you work with chemical solutions in the lab, they're unsaturated solutions. If you go to the carboy or the cart and grab like 1 molarity NaCl solution, that is unsaturated. Versus saturated solutions have to have solid at the bottom, all right? And so this last picture shows, okay, what if we add, you know, take this saturated solution, add more water. Adding more water provides more pure water to dissolve that last bit of solid that's sunk at the bottom. And so that's what happens here. So let's explore saturated solutions. Okay, what is a saturated solution? Okay, the big idea is a saturated solution is a solution with a certain concentration in contact, in equilibrium with undissolved solid, all right, sunk at the bottom of your beaker. So in order to have a saturated solution, you typically need to see solid, and it's surrounded by usually a fairly concentrated dissolved solute around it, all right? So you need both of those at the same time. And so when the solid is in contact with its saturated solution, the aqueous form, we create what's called a dynamic equilibrium, where some of the solid is dissolving to become aqueous, but then some of those aqueous particles are crystallizing back to the solid. Both of these things happen at the same time, at the same rate. And so since they cancel each other out, you observe no net change. But this dynamic equilibrium is happening. Both are reverting back to one another. but we do not see a net change of concentration or solid that's happening. This is called equilibrium, and we will talk about equilibrium for a long time later. Okay. All right, so that is a saturated solution. You need solid, and then you have its aqueous form, its saturated aqueous form in the surrounding solution. That's that big idea. So here, if we have a saturated solution, you can see, oh, if I add more solid to this picture, all right, I add like a big hunk of solid, all I'm doing is adding more solid to this equilibrium, but we don't change the concentration of the surrounding solution because this solution cannot accept more solid. It can't dissolve anymore. All right, so there we go. All right, so we are going to look at different factors that affect solubility, and one of them is temperature. We know if we have more water, we can dissolve more solid. Okay? You know, the difference in between making like 1 liter of Kool-Aid versus 2 liters of Kool-Aid. 2 liters can, in theory, dissolve more stuff. But we can also look at temperature. Generally, for 99% of substances, higher temperature means higher solubility of solids. That water can go in and dissolve solute particles into solution at higher temperatures, like 99% of the time. Sometimes it doesn't, but we'll talk about that later. But yeah, higher temperatures means more kinetic energy. More kinetic energy means that the particles are vibrating more, can go in and break apart those solute particles to make it dissolve. All right, so this graph shows numerically how solubility changes with different temperatures. So what we're looking at are certain concentrations of mixing a certain gram amount of solid to 100 grams of water. So these are all concentrations. All right, so we can look at this graph and see, okay, right around 30 degrees Celsius. So this is 30 degrees. If we look at this line is the saturation line. This is the maximum amount of solid that water can hold at this temperature, if we had 100 grams of water. So if we, let's do this first question. What is the solubility of sodium acetate at 30 degrees Celsius? So that's exactly what I just did. I looked at the 30-degree mark. I cast it over and see, okay, what is that around? 90. All right, 90. So what that means, so that means 90 grams of the solid can dissolve in 100 grams of water. So the solubility of sodium acetate is 90 grams of solid into 100 grams of water. And so that's a concentration unit. All right? That's the maximum that water can hold. Doesn't mean I have to put 90 grams of solid in there, all right? But that's the maximum that it can hold. I like to think that's like water's bucket. That's how big its bucket is, all right? I could put 20 grams of solid in 100 grams of water, but I didn't reach that max point yet where the solution becomes saturated. For fun, because you guys are my second class, so I get to fix mistakes that I did in my first class. So we just said the solubility of this solid is 90 grams in 100 grams of water, but what would how much solid could we dissolve in 50 grams of water? Also 90? No. What's the max 50 grams of water can hold? 45, yeah. So if I only have 50 grams of water, I can only maximum dissolve 45 grams of solid. Are those concentrations different? No, they're the same. They're the same. It's just the ratio is different because, or the amount of solid that dissolves is different because we're working with different amounts of water. Remember, concentration is an intensive property, all right? Volume, mass, those are extensive properties. Right, so this is just our concentration, and we can, depending on how much solvent we're actually working with, can change how much solid we can dissolve. Okay, so that's our saturation line. So if we have a saturated solution, if we measure the concentration of that surrounding solution, we should measure 90 grams of solid for every 100 grams of water, because that's the maximum water can hold at that temperature. Okay, so let's use this graph and determine where on this graph are these points. Let's say we dissolve 50 grams of water in 100 grams, or sorry, 50 grams of solid in 100 grams of water. What kind of solution is that? Where is it on the graph? Is it above the line, below the line, on the line? It is, so 50 grams in 100 grams of water. We're like right here. Okay, so we're below the line. I like to ask myself, can this solution accept more solid? Can I put in a thing of solid? Yeah. So if it can accept more solid, is it saturated? No. This is an unsaturated solution, where unsaturated solutions can accept more solid to be dissolved. I could add 40 more grams, to be exact, right? That I haven't filled my bucket yet. Okay. What if we mixed 100 grams of solid with 100 grams of water at the same temperature? We mix it, we agitate it a lot, and then we are left with solid stuck at the bottom. What kind of solution is this? Supersaturated? No, it's not. Remember, what did I tell you? The maximum that water can hold is, we wrote it, 90 grams, 90 grams. So according to this statement that I said, 100 grams mixed with 100 grams, but you're done mixing, there's solid at the bottom. Did all 100 grams go into the water? No. So how much the solid did go into the water? 90 grams, because that is the saturation point. Just because I mix 100 with 100 doesn't automatically make it supersaturated, because not all 100 grams are going to go into that water. We're dictated by that saturation line. So this solution is saturated, all right? So what this picture would look like is we have our 100 grams of water. We know that this solution maximum can hold 90 grams of solid. So how much solid is going to be sunk at the bottom? 10 grams, all right? 10 grams is the excess that that solution cannot hold. And so it's just gonna be stuck at the bottom, right? And that is a saturated solution. So if I added another 10 grams to this picture, 10 grams of solid to this picture, what would happen to that 10 grams of solid? Would it go into solution? Nope, it's just gonna sink to the bottom, all right? That it's not actually going to change the concentration of the solution that's there, all right? This is saturated, and the key word here is I'm telling you that there is solid stuck at the bottom. That's the key word, yeah. We'll get there, I promise, I promise. Okay, moral of the story, y'all wondering about supersaturated solutions, those are not common at all. Rarely do you work with supersaturated solutions because they are very unstable. You just blink at them and they crash into a saturated solution. They're super unstable, they don't stay there long, they just revert back to the stable saturated solution. But it's in the next slide, I promise, I'll get there. Okay. All right, okay, so let's pretend we mix 90 grams of solid and 100 grams of water. What kind of solution is that? I know the answers are in the corner, but like kind of think your way through it. If you mix these two things together and now you have a solution, will it accept any more solid? So what kind of solution is it? It is also saturated, yep. This is also saturated because it will not, we're right on that line, and it will not accept any more solid, all right? Okay. Okay, so let's, yes, the question, well, how do you make a supersaturated solution? Okay, what's the point of being above this line? So let me just go back here. So I told you if we have a saturated solution, the concentration in the surrounding solution, the actual aqueous part, not the solid, is 90 grams per 100 milliliters. But if we were somehow to trick that solution into holding 100 grams in 100 grams of water, then that would be supersaturated, but you have to trick it. It's very hard to trick the solution to hold more than it actually can because it's super unstable. So this is how you do it. You typically have to heat the solution, all right? To make it, again, these are super uncommon. Like in my last office hours, we spent 45 minutes talking about supersaturated solutions, but I know for a fact there's either gonna be 0 or half a question on supersaturated solutions on the exam, okay? So just so you know. These are super uncommon. So do not automatically think that the solution that we prepare is super saturated, because it's super uncommon. Okay, so how you make one is, let's take a saturated solution first. Okay, so I could take like this picture. All right, this picture, where we have 90 grams in solution, but I have 10 grams of solid sunk at the bottom. Okay, and then I can heat it up. What did we say about our Jello or our Kool-Aid? When we have solid stuck at the bottom, we can get that solid to dissolve if we heat it up. Because what does heating the solution up do? We actually change where we are on this line. So at room temperature, 30 degrees, let's just pretend that's room temperature. This solution can only hold 90 grams of solid. But what about at near boiling, 100 degrees Celsius? This solution can actually hold, I don't know, what does that say? 100, I don't know. It's like 100, let's just say 140 grams, all right? So when we heat up our, Jello mix or our Kool-Aid mix, that's how we're able to get more solid to dissolve, all right? So we can do that here. We can take this solution, this cold solution that has a solubility of 90 grams per 100, heat it up so that we increase the capacity water is able to dissolve solid. So then, remember, we had mixed 100 grams in 100 grams. So at 100 degrees Celsius, so I think that's what this question is right here. If we have 100 grams of solid in 100 grams of water at 100 degrees Celsius, what kind of solution is that? So essentially, I'm taking that beaker, this beaker, and heating it up to 100 degrees. Now, where is it on this graph? We are actually right here in the unsaturated zone. So this is an unsaturated solution at 100 degrees. It's the same stuff, 100 grams and 100 grams, but because we're at a different temperature, water has a different solubility capacity, I'm able to get all that stuff to dissolve. It is unsaturated now. Okay. For fun, before we make a supersaturated solution, if we have this solution, 100 grams and 100 grams at 100 degrees Celsius, if I throw in 10 more grams of solid, what's going to happen? Will it sink to the bottom this time? No, because now water at a higher temperature is able to dissolve more solid, has a bigger bucket. So when I put in 10 grams of extra solid, it will dissolve because we are actually still underneath this saturation line. Okay, I could, in theory, add 30 more grams, right? And it would all dissolve until the solid starts sinking to the bottom. Yeah. Yeah, we are making the assumption that water is not evaporating. We're keeping it at 100 grams. Okay, all right. All right, so, okay, let's go back to 100 grams, 100 grams, right? It's an unsaturated solution. Now, let's slowly cool the solution back down to 30 degrees Celsius. We're going to cool it down so slowly that no solid forms at the bottom. That's the key word. That's the key word. So if we cool it back down, no solid forms. Did the concentration of our solution change at all? No, it is still 100 grams over 100 grams. It's still this concentration, okay? Is that allowed at 30 degrees Celsius? No, we're actually now above that saturation line. So is that solution stable? No, it's not going to stay there long. So that's when we call it supersaturated, all right? That just blinking at it, poking it, will make that last 10 grams fall out of solution, and it'll go back to a stable, saturated state, all right? That's what I mean by tricking it. You have to change the solubility, the maximum, the size of water's bucket really, really slowly, and trick water, essentially not allow any solid particles to precipitate out. You do that by cooling the solution very, very slowly. So no solid crystallizes. And then you have a supersaturated solution for a little bit of time, right? So what happens, so in this picture, you know, how to kind of emphasize the instability of supersaturated solutions, here's a picture of a supersaturated solution of sodium acetate. So essentially they took the solid, heated the solution up, cooled it back down very slowly so nothing crystallized. So in this picture, they're showing just a small little seed crystal of sodium acetate. Once you drop that into the solution, you see all of the excess solute that you tricked into staying in solution falls out of solution. All right, precipitates out until then you have a saturated solution again, which is stable. Right, supersaturated solutions are not stable and they're very hard to make. You can't just mix two things, agitate it a lot, and it become a supersaturated solution. You either have to cool it heat it up, cool it down very slowly, or do actual chemistry to get that to happen. And the thing is, it doesn't stay there very long. All right, so you might have experienced supersaturated solutions. Does anyone know what this is? Rock candy, yeah. So you might have experienced supersaturated solutions in making rock candy, where we heat up water to dissolve a lot of sugar, all right? You heat it up, maybe boil it, all right, to dissolve as much sugar as you can. And then what happens is the point of heating it up is to get all of that sugar to dissolve. But then once that sugary solution starts cooling back down, the solubility of water changes, or that sugar changes, and it falls back down. So if you introduce a stick or a piece of string, those sugar particles that can't stay in the water will start to precipitate slowly on that stick, hopefully slow enough to make a nice crystalline structure. So that's kind of an example maybe of a supersaturated solution that you've interacted with. This one's a little bit better represented. Does anyone know what this is? Has anyone used these? They're reusable hot packs. Yeah, has anyone ever used them? Like in winter sports or whatever. So these reusable hot packs are actually supersaturated solutions of sodium acetate. So they're like these kind of watery packets, and when you want to use them as a hot packet, there's a little piece of metal in there that you click. And then what happens is that the liquid turns into a solid very, very quickly, and a lot of heat is released. That's why it's a hot pack. All right, so right now these things pictured are saturated solutions, but then that clicking of that piece of metal inside that packet, that's the disruption to cause the supersaturated solution to convert into a saturated solution. All right, has anyone ever used these? Yeah? Okay, so once you click it, it turns into a solid. How is it reusable? How can you make it go back so you can use it again? You don't remember. Does anyone, what do? You have to boil it. Yeah, so once you turn the liquid into a solid, it's a saturated solution, you boil it. What does boiling it do? Increase the temperature. So you raise the solubility, so you get it to become unsaturated again. But then it cools back down to room temperature, right? And you tricked it. Now it's staying there in its supersaturated state until you do what? You click the little thing, and then it reverts back to a saturated state, all right? And in the process, you heat is released, all right? And so that is probably the closest example to a supersaturated solution that people interact with. Okay, yeah. No, so the question is making supersaturated solutions at different pressures. No, because solids have very little effect, or pressure has very little effect of solubility of solids in water, but we will look at dissolving other things. What can we dissolve? We can dissolve solids in water, we can dissolve liquids in water, and what else can we dissolve in water? Gases, yes, solids, liquids, gases. We'll talk about all of them, then pressure will be important. Okay, so that is solubility. All right, this slide takes a long time. Okay, so let's take a solid. So this is baking soda. Let's add it to a beaker. We stir it for a long time. And then after we stir it for a long time, we observe a lot of solid remains at the bottom of the beaker. What kind of solution do we have? What? Saturated. Are you sure it's not super saturated? Right, it is not super saturated. You can't make a super saturated solution by just stirring. You cannot. You gotta trick it, right? So this is just a saturated solution. And so I have a picture of that right here, right? Saturated solution. This solution on the outside has a certain concentration dictated by that graph. Let me just draw it in the corner here. All right, there's our graph. Temperature, solubility. And then we have that undissolved solid at the bottom, all right? And they're constantly reverting back to one another, but there's no net change there. So we're gonna do certain changes to this system and think about how does the amount of solid at the bottom of the beaker, does it change or does it not? Or how does the surrounding solution change or not? Okay, so let's try to use our intuition a little bit. Right, so solid, does this solid at the bottom change, or does the concentration of the surrounding solution change? All right, so just think about Kool-Aid and Jell-O. We have solid sunk at the bottom. What does heating it do? It gets it to dissolve. Yeah, it gets it to dissolve. The solid to dissolve. So the solid changes how? The amount decreases, but does that solid disappear? No, where does it go? Into the solution, yeah, so the concentration of the sodiums and the bicarbonates, how does that change at the same time? It increases, yeah, we didn't add or remove any solute or solvent here. All we're doing is changing the temperature. So if we reduce the amount of solid at the bottom of the beaker, it has to go somewhere. And in this case, it dissolves more into the surrounding solution. Why does this happen? Heating the solution changes what? The solubility. We actually change where we are on this graph. And that's the big idea here. We change where we are on this graph, right? So I'm going to write that. Solubility changes. And that is why the concentration of our surrounding solute changes, because we change the maximum water can hold. Okay. All right, so now some more difficult ones. Allowing some of the solution or the water to evaporate. What's going to happen? Let's say, let's do the 100-100 example again. Let's say, the solid is 10 grams. There's 90 grams of solid dissolved in the water, and there's 100 grams of water everything's dissolved in. Okay, what if we evaporate some of the water? So now there's only half the water present. Will all 90 grams of the solid stay dissolved? No. Does evaporating the water change where we are on the graph, where we are on the solubility graph? No, we're still in the same place, but now we've reduced the amount of liquid we have by half. So shouldn't we only be able to hold half in our solution? Yeah. So allowing some of the solution to evaporate actually increases the amount of solid at the bottom, because now we have less water to go ahead and dissolve stuff. But this one's tricky. How does the concentration of the solution change? It actually stays the same. Very good, very good. Why? Why? Did we move on the graph at all? No, we didn't. It's still a saturated solution. We just reduced the amount of water we have available to dissolve stuff by half. The concentration is the same, right? Because remember, concentration is an intensive property. And so all of that excess solute that we can't dissolve anymore just gets sunk at the bottom. So that solid amount increases, concentration stays the same because solubility did not change at all. Yeah?
So for part B, we want to evaporate the water. Doesn't that mean we have to increase the temperature?
Okay, yeah, that's a great question. So the question is, if we evaporate the water, don't we have to boil it, right, or increase the temperature? No, not necessarily. Do you ever just leave cups of water by your bedside? Yeah, what happens over time if you leave it there for weeks and weeks and weeks? It Evaporates, but in your bedroom, does it ever get over 100 degrees Celsius? No. So evaporation can happen at temperatures lower than the boiling point of water because of vapor pressure. Okay, all liquids exert a vapor pressure. We talked about this in Chem 1210. It's why certain liquids are smelly, because they exert high vapor pressures. So things can evaporate under the boiling point temperature. Okay. So that's how solubility, that where we are on the graph, did not change, because we can evaporate at a constant temperature. All right, so let's just take a scoop of water out of this system. Let's just take a scoop of the solution off. How do things change? The solid. Does anything change about the solid? No, it doesn't. Yeah, no, all we did was just take some water off the top. Okay, we just scoop some off the top. Does the concentration of anything change? No. All right, how I say no change, that's what I'm going to say. And then also the solution, no change, because we are removing liquid off the top. We're both removing water and the solute at the same time. B and C are a little bit different, because in B, we remove water, not the solute. But in the second one, because we're just scooping some out, and this is a homogeneous solution, we're actually taking both out with the same concentration. So there's no change to either of those. Okay, let's see if we got this. Cooling the solution. What happens? The amount of solid increases? Yeah, it increases. Yeah. Why? Yeah, I like this. Yeah, we're moving on the graph, right? When we cool stuff down, we're changing the temperature. We're moving where we are on the graph. We're reducing the amount that water can actually dissolve. So the amount of solid at the bottom increases. Okay, but where did it come from? It came from the solution. So what happens to the concentration? It changes, and specifically it decreases. Yeah, because we are going lower on the graph because we're reducing temperature. So see how A and D, they're opposites of one another, because D, cooling, reduces solubility. Well, I feel like we understand that if we've ever worked in the kitchen. Well, A, you heat the solution, you increase solubility of that solid. Okay, all right, these last ones are a little bit tricky. Okay, so let's take this picture, this same picture, right, where we have 100 grams of junk dissolved, but 10 grams of it is at the bottom of the beaker. We have 100 grams of water. Let's add a tiny amount of pure water, just a tiny amount. What does our intuition say when we add more water when there's a little bit of solid sunk at the bottom? Solid dissolves. Yes, the solid dissolves, because we're adding more pure water that can go in and attack and grab those solid particles to dissolve. So how does the solid amount change? It decreases, and this one's tricky. How does the concentration change? Yeah, there's no change, no change, no change. But Dr. N, we just added water. Doesn't adding water dilute junk? Yeah, M1V1. No, but what's the difference here? When we added the water, we're also dissolving solid. Yeah, so that dissolving solid basically brings that concentration back up. So yes, for a split second when you add the water, the concentration goes down. But then solid's going to dissolve to bring it back up to that saturation line. See how I was careful with my language here? I said add a little bit of water. A little bit. Just a little bit. So a little bit, so there's still undissolved solid at the bottom. Because then the last one here is, okay, let's add a butt ton of water, so all of the solid dissolves. So obviously, if all the solid dissolves, the amount of solid decreases, but then what happens to the concentration now? It decreases, yeah. So at this point, we actually have an unsaturated solution, right? We are below the line. Okay, we've added so much water that there's no more solid to dissolve. So that means this solution can actually accept more solid to dissolve if we added some more if we wanted to. And so at this point, now it just becomes an M1V1 calculation, right? Because there's no more solid, excess solid to dissolve into that added water. All right, so that is saturated solutions. Any Any questions? Okay. If you come to office hours, we can talk about it more. All right? Okay. All right. So let's move on. So that section, we looked at dissolving solids in water. We expanded on the solubility tables that, I don't know, maybe at one point when you were in 1210 thought were hard. Now we're going to expand that to, okay, let's look at the solubility of, we just did solids, now let's do liquids, and then last we'll do gases. All right? Because believe it or not, yes, we can dissolve a lot of stuff in mostly water. Okay. So let's look at liquids. Okay, what did we learn Tuesday? That I don't like the statement or like the axiom like dissolves like. I don't like that statement. I mean, like biologists use it, but to me it's an oversimplification, all right? So really I think what they truly mean is, oh, polar substances dissolve in polar substances. Non-polar substances dissolve in non-polar substances. We mentioned this earlier in the chapter when we looked at the energetics of making solutions, but now it's going to come back again, but we're just going to look at it more qualitatively to see, okay, you know, do these two liquids mix, do they not mix? Okay, so let's look at ethanol. Okay, and see some interesting stuff about ethanol here. Okay, ethanol. What intermolecular forces are present in ethanol? Does ethanol have LDF? Yes. Does it have dipole-dipole? Yeah, we look at it. Okay, here's the trick, okay? All right. Things have dipoles, molecules have dipoles when there are really electronegative atoms and they're arranged in a way where their vectors do not cancel. So to find a polar molecule, just look for electronegative atoms. So what atom do we look at in ethanol? Oxygen. And then you look elsewhere in the molecule, is that vector canceled at all? No. So this has to be a polar molecule. Yeah. So yes, it has dipole-dipole. Yeah, so polar atoms, or sorry, electronegative atoms. I always just memorize the high five. Fluorine is the most electronegative. Oxygen, also very electronegative. Nitrogen, also very electronegative. Chlorine, bromine, those are the high five, is what I call them. Fluorine, oxygen, nitrogen, chlorine, bromine. That's 5. Yes. While everything else is just less electronegative. All right, any other IMFs here? Yay, hydrogen bonding. Yes, hydrogen bonding. And so which hydrogen? Are all the hydrogens? No, only one of them. It's the one in that OH group. Great, okay. So, ethanol, I'm just going to tell you, infinitely dissolves in water. What does that mean? It means I can take any proportion, any ratio of water and ethanol, and they will always dissolve in one another. But when we talk about liquids, the language we should be using is miscible. I know when we talked about solids dissolving, we said, oh, salt is soluble in water. But we say ethanol is miscible in water because it's liquids, and that's just the language chemists use, all right? So when two liquids dissolve, we say they're miscible. Okay. So ethanol is infinitely soluble in water. Why do you think? Why do you think? Hydrogen bonding, yeah, very good. Both of them have the ability to hydrogen bond. They can hydrogen bond with themselves. So then therefore they can hydrogen bond with one another. So that makes sense why they can mix with one another, because they have similar IMFs. So like dissolves like works here, that's fine. Right, they have similar IMFs. Okay, but the interesting thing is that ethanol also is infinitely soluble in, what is this, hexane. Hexane is a hydrocarbon. So what is the only IMF present in hexane? Just LDF. Does, because it's nonpolar, does hexane do dipole-dipole? Does it do hydrogen bonding? Nope. But why on earth does ethanol also dissolve in hexane? So let's look at the other parts of ethanol. Ethanol has an OH group, but it also has this cool little hydrocarbon part that is also nonpolar. So we need to consider the entire structure here. So we see ethanol kind of has this duality. The OH group interacts strongly with water, but the hydrocarbon tail on ethanol also can interact with nonpolar substances like hexane, right? And so that is what makes ethanol kind of bipolar in a sense, where it can interact with both. Although, so this is kind of where the axiom like dissolves like kind of breaks down a little bit, because ethanol, it can dissolve in both. While, like dissolves like would think, oh, it would only dissolve in one of them, okay? So that's kind of interesting there. So when liquids completely dissolve in one another, they will make one uniform liquid. Like if you look at a mixture of ethanol and water, it's going to just look like water. But if you have two liquids that are immiscible, like do oil and vinegar mix? No, they don't. And so what that means is when you mix oil and vinegar, it makes layers. They don't mix, and then just based upon densities, they will float on top of one another. So here's an example where you see distinct layers, and they're heterogeneous, all right? And so the ordering of the layers has to do with densities. But the reason, so does the reason that these liquids don't mix, like, so what is that? Hexane water and CCl4. The reason they don't mix, is it because of their density differences or because of something else? Why don't those layers mix? It's not because of their density differences. What did we learn on this slide? It's because their IMFs are different, yeah. Yes. All right, so let's keep going. Yeah, again, like dissolves like works, I guess, but really at the soul of it, it's matching IMFs, create strong attractions. That is what produces homogeneous solutions, right? So again, we already looked at this slide earlier, or these pictures. We want to look for matching IMFs. Two nonpolar substances. In the case of liquids, we say they're miscible, or if it was solids, we can say they're soluble. Two things that are polar, two things with hydrogen bonding, or our weird one, the reason why salt dissolves in water is not because like dissolves like, but because of why? Ion dipole, yes. Water will dissolve salt because of ion dipole. That's the one weird one where like dissolve like does not work. Yes, right there. Okay. All right, so let's look at some pictures. Okay. When looking at structures, it's fine to just think of like dissolves like. That's a good way to kind of generally understand what IMFs are occurring here. So I have a bunch of stuff and their structures here. So if you squint your eyes and think, okay, like dissolves like, you'll be fine here. All right, hexane and water, do they mix? Do they mix? No. No, they don't mix. Why? Mismatch IMFs. Hexane, its strongest IMF is London dispersion. Water's is hydrogen bonding, and you can just look at the structures. They look nothing alike, okay? Versus, let's do the third one, hexane and dodecane. Do you think those will mix? Don't think about it that hard. Yeah, they'll mix. Yes, they mix. They look just like each other, but really it's because both of them have LDF as their strongest IMF. All right, what about ethanol and water? Will they mix? Yes, you see the little oxygen on ethanol, and water also has that oxygen. All right, we already looked at those structures here. These do mix because the reason both of them have hydrogen bonding. If they can hydrogen bond with itself, that means they can hydrogen bond with each other. Okay, and then last one, ethanol and dodecane. Just squint your eyes. Do you think they mix? Yes, they do mix, yes, because ethanol has that nonpolar tail, and dodecane is also very, very nonpolar. So the reason that these two mix is because of LDF. Okay. All right, before I do the next one, okay, so back in COVID era, what did we use all the time during COVID, other than masks? Hand sanitizer, yeah. Okay, hand sanitizer is made primarily of Ethanol, yeah. And so let me just bring back the structure of ethanol. Okay, what happens, okay, don't look, so what happens when you use too much hand sanitizer throughout the day? Your hands get dry. Yeah, why do they get dry? Because it strips all your water away. Yeah, that's one reason. It strips all your water away. What else? Ethanol can also interact not only with polar things, but non-polar things such as oil. Yeah, so ethanol, it's kind of like dual purpose. Why it dries you out so much is because it strips the water away and it strips your protective oily layer on the top of your skin to keep all of that moisture in. So it strips all that oil away as well. So don't use too much hand sanitizer. The ethanol is meant to do the disinfecting, but just using too much, will give you all the cracked skin and all of that. And again, it has to do with the, dual parts of ethanol. We look at both of the IMFs there that we can see, oh yeah, it can interact with both water and non-polar things like oil. All right, so let me tell my story. Has anyone ever used this ISO heat? You buy it from Walmart for like $2.50. Put it in your gas tank of your car. Okay, well maybe you all should. This is a lesson for all of you. Okay, every winter, everyone should maybe like at least once a winter, maybe once a month, especially in the winter, put a tube of this ISO heat into your gas tank when you drive. Right? It's really important during the cold weather to do that. So let me set the stage. I was graduating with my PhD here, and so leading up to it, I think I left my car outside. It rained really hard, and I left the gas cap off. Yeah, it was like a day or two before I was meant to graduate, like walk. Walk it was over the winter, so I did it in the shot. But my family was over. Like my dad, my mom, my brothers, my husband's family was here to watch me walk, all right, all of them. And so imagine, okay, I did that to my car, and then the morning of graduation, I was about to walk. When you too one day walk, you will experience this as the walker, the graduating person. You have to arrive like an hour or two before everyone else. So like my family was coming later, but I had to drive into school first. And so imagine me, we're having breakfast together, enjoying each other's company. I go to start my car and it wouldn't start. It wouldn't start. And then so imagine my dad, my husband's dad, my brothers, all out there around my car trying to get it to start, all right, trying to troubleshoot, make sure that I go to graduation on time. And I realized it's because I left the gas cap to my car open, all right? And so it rained the other day, so a lot of water got into my gas tank. And when there's water in your gas tank, it causes a lot of problems because water is more dense than gasoline. Gasoline is basically octane. It's non-polar, so does water and gasoline mix? No. So water sinks to the bottom of your gas tank where the fuel line is. So instead of when I turn over my car, it inject gasoline into my engine, what was it throwing into my engine instead? Water. And that's bad, okay? Because is water combustible? No, and that's why my car didn't start. So we figured it out. I did graduate on time. Okay, this is what we did. Thankfully I had a bottle of ISO heat in the garage. I put it in my gas tank, okay, knowing that ISO heat is like ethanol. It's actually a different alcohol. It's isopropanol, where we have this OH group that interacts strongly with the water, but then we also have the hydrocarbon chain that interacts with the ethanol, octane. So I put that in my gas tank, and literally every man in my family was out there shaking my car. Like 2 people on the hood, 2 people on the trunk. They're literally like trying to agitate my car to try to get the ISO heat to mix the water and the octane or the gasoline. So the next time I turned over my car, it would have enough gasoline to start my engine. And it worked, okay, it worked, right? So, that's the power of, alcohols like this that have both a polar and non-polar end. It's able to do stuff like that. All right, so I mentioned, doing this in the winter is really important because it's common that a lot of moisture can get into your gas tank. If you have trouble starting over your car, that might be a reason. I usually do some of this with every fill up in the winter. Because why not? Why not? Get rid of that water. Okay, so that's my fun story. All right, one more. I like talking about cars, but I guess for my other people out there, my bio people out there. Okay, I got 2 vitamins here. Okay, one of these vitamins is water soluble and quickly excretes out of the body when you ingest it. The other one, the other vitamin, is stored in body fat and stays around for a long time. Which one do you think is stored in body fat? Vitamin A, yes, vitamin A. And what, is that something you just memorize? No. What did you look for? IMFs, yeah, so we see vitamin A has a lot of nonpolar parts. Oh, but we do see one OH group on vitamin A. But what's the difference with vitamin C? Tons of OH groups. Yeah, so we see that, vitamin C has a strong affinity for water, while vitamin A not so much because it's much more nonpolar. All right? But let's just check ourselves. Let's remind ourselves what vitamin A and vitamin C look like in the vitamin form, or like the supplement form. Vitamin A, if you've ever taken them, are those like little jelly packets. Okay, I imagine, I never did this myself, but if you take a vitamin A packet, maybe like snip the gelatin packet apart, it probably will not dissolve in water, is what I'm assuming. It'll probably just float or sink to the bottom of your water if you were to cut one of those packets open. So you can see how it has much more affinity towards oils rather than water. Versus vitamin C, the most common way that we ingest that, like I almost take one every day, is like an emergency packet that dissolves in water, right? And that makes sense due to the structure of vitamin C. Tons and tons of OH groups where you got high attractions with water, right? So these aren't things to memorize. We get a lot of this stuff from the structure and us understanding IMFs to get there. Okay, last one. Let's predict, using what we've learned of matching IMFs, when things mix, do these things mix? Whether they be 2 liquids, solid and a liquid, let's just think, will these 2 things mix? All right, chlorine gas and benzene, will they mix? Do you think they'll mix? No? What are we looking for again? Matching IMFs. Chlorine is what kind of molecule? Non-polar, so it's LDF. And then benzene, also non-polar, so will these mix? Yes, they will, because of LDF. Okay, this one's a little bit trickier. Ammonium nitrate and water, will they mix? Yes. Why? Ion dipole. Yeah, so the tricky part is, you might be thinking, but doctor, and they look nothing alike. But ammonium nitrate is our special case. It's no different than salt, okay? Where we have a cation and anion, there are ions for ion dipole, which is very strong, and water is our dipole for ion dipole. So yes, these 2 things mix. What about the same thing, this salt or CCl4? Will those mix? Yes or no? We made ion dipole in the previous one. Can we make ion dipole here? Does anything have a dipole? Nope, so this does not mix. Yes, we have ions, but CCl4 is nonpolar, so it cannot do ion dipole, so it's not going to mix. All right? All right, that thing and octane. It looks like an alcohol and octane. Will they mix? Yeah, probably, because you see, there's a long tail. Yes, there's an OH group, but octane also has a bunch of carbons and hydrogens, so yes, this will mix because of LDF. But will this alcohol mix in water, do you think? Yes, it will also because of that OH group. I mean, at least a little bit of it will. All right, oil and vinegar, will it mix? Nope. What about oil and hand sanitizer? Yes, it will. Yeah, we learned hand sanitizer is ethanol, kind of like this molecule here. Oil is essentially like octane nonpolar. Ethanol has that carbon tail to interact with. So yes, that will mix because of LDF. Right, so those are the things we want to look for. All right. Okay, so that is mixing liquids in usually water, okay? So again, we're just looking for matching IMFs. So let's look at the last one. We did, let's dissolve solids in water, let's dissolve liquids in water, now let's dissolve gases in water, yes. So solids, for the most part, we saw with saturated solutions, solids get more soluble at higher temperatures. The water molecules, they're vibrating more. If they're vibrating more, they can get in there and grab those solid particles and turn them into a solution. They can dissolve them. It's different for gases. But before I go there, so I will say 99% of solids are more soluble at higher temperatures. There's like 0.5% that actually become less soluble at higher temperatures. But again, that's super rare, all right? And you might be asking, well, why? And it's because of entropy. Entropy is like my magic wand that explains weird phenomena, but we will explain everything and explain entropy in chapter 19. And then it will all be unveiled, and you'll be amazed. So just for now, just know 99% of solids become more soluble at higher temperatures. But gases, on the other hand, are different. All right, so you might be thinking, gases in water, gases dissolved in liquid, that's so weird. But have you ever enjoyed a soda? Yes. Why do we enjoy soda? It's carbonated, it's yummy, the sugar, all of that. So that carbonation, what you're actually tasting are tiny little CO2 bubbles that are dissolved in that solution, the soda solution. So you do, in fact, experience gases dissolved in water. So how else do you think fish breathe? All right, they get the oxygen that's dissolved in the water. So the trends with gases are actually opposite of solids. Gases become less soluble at higher temperatures. Same reason as solids. At higher temperature, there's more kinetic energy. Gases at higher temperature, they're moving faster. They have greater kinetic energy. And so gases are different than solids, where gases can actually leave the solution. So if a gas has more kinetic energy, it's more likely that it can leave the solution and go flat, right? Again, comparing it to soda, go flat is when the gas leaves the solution. All right, so you see that here. Highest solubilities are at low temperatures, less soluble at high temperatures. I can also relate this to something else. What would you rather drink? A hot soda or a cold soda? Cold soda. Have you ever drank a soda so cold, you open, it's a hot day, you drink it, and it's like, dang, that's spicy. You know what I'm talking about? Yeah, that it's so cold that the CO2 burns your tongue. Yeah, and so relate that to solubility, okay? The soda is so cold that there's so much dissolved CO2 in the solution that it burns your tongue. Yeah, versus the experience isn't as intense when the soda is warm, because warm sodas hold less CO2 in that solution. So it won't feel as carbonated as a cold soda, right? So yeah, temperature and solubility. So you have experienced that. What about different gases? So the question is, do different gases have different solubilities in water? Yes, they do. So we see that in this graph here. Methane seems to be the most soluble in water, helium not so much. We can also see that here. Here's solubilities at the same temperature, but the trend is, as the gas has more intermolecular forces in the sample, the gas sample, the more soluble it is. Because the more attraction that gases have to one another, the more attraction there will be to the water itself to keep it in that solution. So we see in this table, the trend is as molar mass increases, we see solubility of the gas increase. And so for the most part, when molar mass increases, intermolecular forces increase due to which one of our intermolecular forces that we track with molar mass? LDF, yeah, so that's what we see here. We see LDF increases because molar mass increases, so IMF increases, so the heavier gas particles tend to be more soluble in water, all right? So those are the two trends. Okay, so let's put it all together, all of it, okay. Where we're gonna look at different comparisons of solubility. So here, which Starbucks drink has the capacity to be sweeter, meaning hold more sugar? A cold one or a hot one? So what you're doing is using the relationship between solubility of a solid, sugar, and temperature. So which one can, in theory, be sweeter? The hot one. Yep, the hot one. Yep, solids become more soluble at higher temperature. Which soda is going to go flat first, the hot soda or the cold soda? Hot soda, yep, because that one has more overall kinetic energy. Gas particles are moving faster. They're more likely to leave the solution versus the cold one, less kinetic energy. Less energy to overcome to leave that solution. All right, this one's a little bit different, but similar. Here, we're also looking at solubility of gases, but this time we're looking at the solubility of CO2 gas versus nitrogen gas. All right, there's two classes of beer. There's like normal beer that is made of CO2. CO2 is the carbonation, but then there's other beers out there like Guinness. Guinness is different, where the bubbles is not made of CO2, but it's made of nitrogen gas instead, all right? We were in office hours talking about this. There's other examples of this. Apparently there's a nitrogen-based Pepsi. Has anyone tried that? Or cold brew? Or there's, apparently there's a nitrogen-based Monster also, I was told, okay, Monster energy drink. For the most part, when we think of like tasty carbonated beverages, we're thinking CO2. But again, there's a smaller class of drinks out there that are, instead of CO2, they use nitrogen. That's the whole gist here. So which one is gonna go flat first? CO2-based things or nitrogen-based drinks? I put the molar masses up there. Maybe they're important. I don't know. What do you think? Which one goes flat first? Nitrogen or CO2? Nitrogen, yeah, nitrogen. It's lighter. It's lighter, so less IMFs, less likely to stay attracted to the solution itself. Okay, I was told, we were talking about this for a while. Someone said that they had tried the nitrogen-based Monster, and they said it tasted already flat. And the reason is because nitrogen is, so CO2 is actually a weak acid. So when we drink it, we're literally tasting like the acidic properties of CO2. Nitrogen does not have that. So that's why it tastes flat, because it's not acidic. He said it was not good. Right? He said if you're sensitive to the bubbly, then maybe it would be good. Okay. All right, so gases, we said properties, solubility of gases, trends with temperature, trends with IMFs, depending on the weight. But then the last thing that affects solubility of gases is the pressure on it. So let me ask you this. You know, you leave a soda out on the table, it eventually goes flat, right? But if you have a can of soda and it's unopened, will it go flat? No, because an unopened can of soda is packed under pressure. And so there's this higher pressure inside the can, it does not go flat until you open it. Opening the can exposes the can to regular pressure, 1 atmosphere pressure, and now that soda has the opportunity to go flat once you open it. So that's the whole idea here. Higher pressures, higher solubility of gases, all right? So that's where Henry's law comes into play. The solubility of a gas is proportional to a constant that's usually given to you, times the partial pressure of that gas in contact with the solution. So higher pressures, higher solubility, all right? So in a can, there's high pressure of CO2, so that's why it's all carbonated in the can. But once you bring it out to the atmosphere, now that's low pressure of CO2. Now that soda will slowly become flat over time because now you've reduced the partial pressure of CO2 in contact with that soda. So this equation, the next two slides, we'll be using this equation where S stands for solubility, but really this is concentration in molarity of that gas. Usually the unit is molarity, right? Equal to K, Henry's law constant for that particular gas. So different gases have different Ks. A gas at different temperatures will also have different Ks, right? So times the partial pressure of that gas above the liquid. So let's do a question. So, soda. What pressure of CO2 in atmospheres is required to keep the dissolved CO2 in soda at 0.12 molarity at this temperature? And I tell you Henry's law is constant. So it looks like I give you solubility, I give you K. We are solving for the partial pressure of CO2 required to keep all of that there. So it's just plug and chug, all right? So let's put this together. So again, solubility of that gas is just concentration in molarity. And I'll show you how those units work out. So solubility of CO2 is given as 12.12 molarity equals the Henry's law constant, so 3.4 times 10 to the negative 2 molarity ATM. We are solving for partial pressure of CO2. Right, one variable, you can solve that. But when we solve for partial pressure of CO2, what unit is it going to have for pressure? ATM. Yeah, molarities cancel. ATM is there in the constant unit, so we can see the pressure that comes out is in atmospheres. And so when you calculate that, you get 3.5 atmospheres. All right, so a soda is packed in almost 4 times that of external pressure. So when you crack open that soda can, you release that pressure, and then now your soda will go flat over time. Okay, so that one's simply plug or chug, plug and chug. So we'll do a slightly harder one. I think I have time to do it. Yeah. But let's do some quicker conceptual ones. All right, which one of these pairs, of these 3 questions, has more dissolved nitrogen, more dissolved gas? An open container at 50 degrees or 2 degrees Celsius? What do you think? 2 degrees, yeah, because gas is more soluble at lower temperature. All right, water now in a closed container in contact with half an atmosphere of pure nitrogen or 1 atmosphere of pure nitrogen. Which one has more dissolved nitrogen? 1 atmosphere, yeah, because remember, Henry's law is constant. Solubility, the amount of gas dissolved, is proportional to the pressure above it. So here, in this first one, there's only half an atmosphere of nitrogen. In the lower one, there's 1 atmosphere of nitrogen. So yeah, this one's going to have more dissolved CO2. Okay, this one's a little trickier. Water in a closed container under 2 atmospheres of pressure, but only half of the particles are nitrogen, or 4 atmospheres of pressure, but 20% of the particles are nitrogen. Which one has more dissolved nitrogen? A lot of folks will just say 4, the 4 ATM, because higher pressure, right? But is all of that 4 ATM nitrogen? Nah. So we got to use the Dalton's law of partial pressure. Pressure of a gas is equal to the total pressure of the system times the mole fraction of that gas. So if the total pressure is 2 atmospheres, the mole fraction is half. What is the partial pressure of just nitrogen? 1. Yes, I tried to make them easy numbers without a calculator. Okay, then the last one, 4 atmospheres of pressure, but 20% of it's nitrogen. So the partial pressure of nitrogen in that system is 0.8 ATM. Yeah, so now which one has more dissolved nitrogen? It's the 2 ATM one, yes, because you're looking at partial pressure of the gas in question. All right, good. We have enough time to do the last question. And that's, you might see, okay, we just did Henry's Law equation. This one was straightforward, plug or chug. But the idea here is that I gave you, recalculated the partial pressure of pure CO2, all right? But is CO2 and it's pure, is it pure in our air? No, our air has a lot of stuff in it. So the solubility of these gases is proportional to the mole fractions that are present there. So let's do this last one. We got five minutes, right? Yes, okay. We have Henry's Law as constant for, we're doing nitrogen again. Yeah, this should say nitrogen, sorry. We're still using this equation, but we're doing it for nitrogen. So I'm giving you Henry's Law as constant for nitrogen and the mole fraction of nitrogen in air. It's 80% nitrogen in air, all right? Okay, I'm asking you, how many grams of nitrogen is dissolved in 50 liters of water that is in contact with air pressurized to 5 atmospheres? Ooh, there's a lot going on here. But I recognize these numbers, right? It looks like, oh, yeah, here's Henry's Law as constant, I know that. We're given a pressure, so it looks like I can calculate solubility of nitrogen. But there's a problem, okay? So think about this. The pressure that we put in Henry's Law has to be the pressure of that gas. So is 5 atmospheres the pressure of nitrogen in the sample? No. I gave you the mole fraction of nitrogen. So air, in this example, we have 5 atmospheres of it. But the mole fraction of nitrogen is 80%. So what is the partial pressure of nitrogen in this air sample? It's not 5 atm, it's whatever 80% of 5 is, which is 4, yes. So this sample, only nitrogen is exerting 4 atmospheres of pressure, all right? So does that 4 go into Henry's Law? Yes, it does. It does, because that is the partial pressure of nitrogen. We want to get the solubility of nitrogen. So we use the partial pressure of nitrogen. So yes, we put in that 4 atmospheres. And by doing that, we can solve for the solubility of nitrogen. So put those numbers together, 6.4 times 10 to the negative 4 molarity ATM times 4 atmospheres. So this solution has a concentration of 0.00256 molarity nitrogen gas. All right. When air is 80% nitrogen, I give you Henry's Law as constant, and we pressurize the system to 5 atmospheres. Is that my answer? Nope. This question asks for what? Not molarity of this sample, but grams. So what we just did, new stuff. Henry's Law. Now, what we have to do to convert our answer to the right answer, this is all review. So molarity has what unit? Moles per liter. So this answer means that there is 0.00256 moles of nitrogen in 1 liter of solution. Do we have 1 liter of solution? Nope, we have 50. So 50 liters times, now let's use molarity. The 1 liter is going to go on the bottom. And then we put 0.00256 moles of nitrogen up top. If we end right there, we would calculate the number of moles of nitrogen in the sample, but we don't want that. We want grams. So now what do we use? How do we go from moles to grams? Molar mass, yeah. So I give you, it's 28 grams per mole. Where does the 28 go? On the top, because 1 mole goes on the bottom, 28 grams of this N2 goes on top, and that's how we get our answer, that this system has 3.6 grams of nitrogen gas in it with this information. All right, so we will pick up here on Tuesday. Have a great weekend. Oh yeah, I still have office hours in Fontana, thank you.